gosh, this factorial function pops up in the strangest locations. Now, let's write down in factorial. And remember, it's just the product of the first n positive integers. So you can write this using product notation. Now, this product notation is not quite as common as summation notation, but it is convenient. So we have I equals 1, so 1 there to n of I. And y'all remember, this is just the very same thing as 1 times 2 times 3 dot dot, thank goodness for ellipses. Okay. So y'all, this in factorial, it means this, but you give that to college algebra class and they go, what? Because this is not a common symbol at that level, I don't think. Okay, so what we want to show is that the product of I raised to the 5th power is actually congruent to n factorial mod 10. Okay, now this is really fairly straightforward if you believe this lemma, which is kind of interesting. It says that if you raise any integer to the 5th power, it's going to end in the same digit as the integer. Okay, and it's a nice, it's kind of a recreational math result, but the rigor behind it is that if 2 and 5 are the only factors of 10, and this is a divisibility result. This says I to the 5th minus I is divisible by 10. So if you can prove I to the 5th minus I is divisible by 2 and I to the 5th minus I is divisible by 5, you'll get this result. Okay, and this is immediate. All you have to do in mod 2 is check I equals 0, and it's clearly true for both cases. I equals 0. And let me put 1. Remember, 0 and 1 are the only possible remainders when you divide an integer by 2. So that's why these are the only two integers you have to check. And it's clearly true, trivially true. If you put 0 in here, you get 0. You put 1 in, you still get 0 and 2. Everything divides 0, right? Now this result's slightly deeper. You can check it for 0, 1, 2, 3, 4, or you can just note this is in the relatively famous Fermat's little theorem, I think. A to the p is congruent to a mod p. And this is for all a. You don't have to even have the relatively prime condition going on here. Okay, so mod p. Okay. And this is exactly that form, so we're done. Now again, if you don't trust, this is called Fermat's little theorem. This is called FLT right here. If you don't trust it, just all you have to do is check for 0, 1, 2, 3, and 4. That's what they call a complete residue system, I think. Okay, now, so what have we done? Well, we've shown that I to the 5th is congruent to I mod. We've shown this limit. We've established this limit since we've done it for 2 and 5, and 2 and 5 are the only divisors of 10. So this lemma right here is true, and all you have to do right here is just rewrite this. You know, you can replace it. This is congruent to of just I, right? But you've seen earlier that this is just another way of writing down the definition of n factorial. Okay, so that proves it. Now guys, you may not want to stick around for this, but I'm going to go ahead and I'm going to work through a concrete example. Let's say we did n equals to, I don't know, 4. Okay, so let's do n equals 4 here. So what does that mean? We would get that this leads to, I'll leave out the 1, of course, it's not important. 2 to the 5th times 3 to the 5th. And you can actually see this. You might think you need a calculator, but you don't on these kind of problems, really. Times 4 to the 5th, right? That's exactly what this part is right here, right? Now, we're saying it's congruent to 4 factorial. Okay, we're saying that it is congruent to 4 factorial, or 24. So let's just write this. Congruent to 4 factorial. Okay. Now, so how would you go about establishing this? Well, this is equal to 24. Now, however you want to cut this, but maybe a better way of thinking about this would be just consider this as, let's see, what is this? 2 cubed times 3? 2 cubed times 3 is what this is equal to, right? And so you see, folks, when you subtract these two things from each other, which is what congruence is, and check to see if it's a multiple, it's very easy to get this. Let's go ahead and write this down. So you would have 2 to the 5th. It's just kind of tedious to write it down. Keep saying it's easy, but at least we're not having to use a calculator. 2 to the 5th minus times 3 to the 5th times 4 to the 5th. And you'll notice that would just change this. What is this? This would be 2 to the 10th. So this is equal to 2 to the 15th, right? It's kind of cool. And you're not having to know how to pronounce any of these numbers or do any calculations here. And of course, y'all, that came from the fact that 4 is equal to 2 you multiply, and then you add your exponents, and you get this, okay? So now, if you go this, we're trying to show that this is divisible by 10, all right? So we're trying to show that this result right here, again, y'all, this is tedious, but it's just algebraic manipulation with laws of exponents. Now notice you can factor out 2 cubed times 3, which is, you can see the pattern here, 2 cubed times 3. Now what's left here, folks? Well, 2 to the 12th is left. Two to the 12th times 3 to the 4th minus 1. But y'all notice this is equal to 4 factorial. Remember, this is equal to 4 factorial. So it's a multiple. This object here is a multiple of 4 factorial, which is absolutely equivalent. A lot of people don't like congruence because they don't believe it. But this means that if you subtract this from this, it's going to be a multiple of, I'm sorry, I should have said 10 here. Let's see, is that a multiple of 10? 2 times 5, this is 2. We have to know the last digit of this. So it's not quite as easy as I was saying. We're trying to show that it's a multiple of 10. And what I'm showing you here is not quite as clear. So yeah, you would have, it's not an as easy computation as I thought. But there's a way to use reasoning and last digit analysis right here. You can use, there's things you can use here to figure out what the last digit here is, what, 1? Yeah, here you go. The last digit here is 1, all right? And then what's the last digit of 2 to the 12th? Okay, well, we know that 2 to the 10th is 24, 1,024. Then you do it again, 8, 6, okay? So y'all, you see right here, this would be a multiple of 5 right here, okay? This object right here, let me write it underneath. You can do what they call last digit analysis. This is a multiple of 5. Right? but we certainly have a multiple of 2 out here, don't we? So you see, we do have that this is congruent to 0, modulo 10. And that took a little bit of time, folks, but hopefully it models just what you have to go through sometimes. That's mod 10. Let me write it underneath. Again, y'all, the key aspect of this without using a calculator, really, well, I guess, really, if you're going to talk about 2 to the 12th, but you can figure out the last digit of 2 to the 12th pretty easily. Like, for example, 2 to the 12th is 2 to the 4th cubed, right? 2 to the 4th cubed. Well, 2 to the 4th, no, I'm sorry, wait a minute. 2, I think you would just have to do, let's see, 2 cubed. 2 cubed is what, 8? 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th ends in 12, ends in 2. So this part would end in 4. Yeah, you see, folks, this would work out. Just check it out. You can verify that this is a multiple of 5 by doing last digit analysis. But anyway, you don't really have to do that, but it's kind of nice to see that it's possible without doing a lot of calculator or technology assisted calculations. All right. Okay, that is all. Till next time.